A developer today can stitch together a functional, complex application over a single weekend for a few dollars in API credits. Generative tools remove the need to hire a massive engineering team to write boilerplate code up front. This effectively collapses the traditional capital expenditure, the upfront cost of building a product. This shift creates a different financial burden. Instead of paying to build the system once, you pay to run every single feature, every single time. The cost moves from a static asset to a compounding operational expense. While these usage-based fees are negligible during a 10-user pilot, they begin to outpace revenue growth as soon as the user base reaches 10,000. Each user interaction triggers a sequence of back-end compute operations. In this model, every click is a billable event. Software costs haven't vanished. They are now deferred until the product begins to scale, creating a direct link between user growth and infrastructure debt. To understand how these margins erode, we have to look inside a single AI interaction and map the infrastructure it requires. For technical founders and engineering leaders, managing this architectural cost is the primary factor in reaching sustainable unit economics. Share this video with your founders and engineering teams, and subscribe to Lalit Official for more system-level architecture breakdowns. Unchecked infrastructure costs can make it impossible for a growing startup to reach profitability. Mastering architectural cost control is now a requirement for engineering leadership. These charts compare two economic life cycles. Traditional software requires high capital to build, but its operational cost remains low and predictable. Conversely, generative systems are cheap to prototype, but the cost to operate them curves exponentially upward as user requests grow. This creates the toil shift, the manual, repetitive labor needed to keep a system running. AI tools generate high volumes of code, but that code often lacks architectural coherence. This creates a backlog of technical debt that humans must eventually resolve. This review burden falls on senior developers. Instead of designing new features, they spend their time auditing and reworking AI output, which causes a measurable drop in their original productivity. Rapid code generation masks a growing operational debt. The time saved during development is lost to the maintenance required to keep the system stable. Every prompt initiates a sequence of discrete, billable compute tasks across multiple systems. First, the request hits a vector database for context, adding cost. It moves to a prompt builder, swelling the payload. Next, the foundation model processes inference, the most expensive step. Finally, external tool calls and hallucination evaluators add unpredictable latency and final charges. This multi-model process repeats for every interaction, causing costs to compound. A simple chat interface hides an expensive supply chain. What feels like a conversation is actually a multi-node compute pipeline with a mounting bill. To maintain these systems, companies face a mandatory observability burden, measuring a system's internal state by looking at the data it generates. Because AI responses are probabilistic, meaning they change even with the same input, traditional error logs cannot explain why a system failed. Reliability requires capturing detailed traces to follow the exact reasoning path the model took. Storing and analyzing these traces, along with monitoring for hallucination rates, creates a second massive layer of infrastructure cost. Engineering teams end up paying twice, once to run the AI models, and again for the high-volume data processing required to understand their behavior. This is why investors scrutinize thin wrappers, products that rely entirely on external APIs. Dependency on external models leads to high operational overhead, leaving the company with thin profit margins. If you are seeing these economic shifts in your projects, like the video and type "vibe coding" in the comments. Rapid user growth without architectural cost control can lead to negative margins. Scaling a product today requires a strategy for managing these recurring compute fees. Solving this requires engineering teams to treat cost as a first-class architectural concern, equal to system speed or security. Every feature must be measured by its specific cost per interaction before it goes to production. We can intercept the supply chain using a semantic cache. A semantic cache stores previous answers and serves them when a new user asks a mathematically similar question, stopping the meter before it reaches the model. This drastically reduces redundant computations. Requests that miss the cache hit an AI router. Not every user question requires a generalized model. Hybrid systems that use standard code for simple tasks are far more cost-effective. Routing basic tasks to deterministic code or small, specialized models preserves the expensive frontier models for deep reasoning. Efficient architecture is designed to prevent data from ever reaching the most expensive nodes in the supply chain unless it is necessary. We must also optimize the observability fire hose mentioned earlier. Logging every token and trace for every single interaction is too expensive at scale. Instead, teams can use intelligent sampling and data aggregation to capture system health without recording every transaction. A mature AI system uses dynamic valves to monitor reliability, securing the production environment without doubling the infrastructure bill. Software has transitioned from a build-once capital asset to a pay-per-use utility. This requires a new definition for the minimum viable product, or MVP. A modern MVP proves user value alongside a sustainable, scalable operational cost. Engineering execution and business strategy must align around token efficiency and pipeline optimization. Building AI features is only the starting point. The core engineering challenge of this decade is sustaining them profitably.